Every July, beaches across the Northern Hemisphere fill with people escaping the heat. We alter our environments, clothing, and habits to survive the peak temperatures of summer. Why do we see this drastic shift in temperature, daylight, and shadows, arriving on a predictable, repeating schedule every 12 months? The Earth spins on its axis once every 24 hours. This motion, called rotation, is what dictates our daily cycle of light and dark. But while the Earth spins, it also travels. It moves along an orbital path around the Sun, a journey called revolution that takes exactly 365.25 days to complete. Looking at this orbit, it is tempting to assume that summer happens when Earth physically moves closer to the heat source, but the data contradicts that entirely. Earth actually reaches its closest orbital point to the Sun, a position known as perihelion, in early January. This happens exactly when the Northern Hemisphere is covered in ice and experiencing its coldest temperatures. Since our closest proximity to the Sun aligns with freezing winter weather in the north, physical distance cannot be the driver of our seasons. A different mechanical variable must be responsible. Earth does not sit perfectly vertical. Its axis leans at a strict 23.5-degree angle, and as the planet travels through space, this tilt remains fixed, continuously pointing toward the North Star. This animated diagram shows exactly why that angle matters. When a beam of light strikes a flat surface head-on at 90 degrees, its energy is highly concentrated. But when that same beam hits at a 45-degree angle, the energy spreads out over a much wider, diffuse area. Apply that geometry to the planet. The hemisphere leaning toward the Sun intercepts the incoming solar radiation head-on. The light is concentrated, delivering intense heat to that specific half of the globe. Meanwhile, the hemisphere leaning away forces the incoming light to strike at a steep slant. The exact same amount of solar energy is stretched across a much larger surface area, diluting the heat. Earth's rigid, unmoving tilt dictates exactly where that solar energy concentrates and where it dilutes. That uneven distribution of heat creates the massive temperature divides we experience as seasons. Watch what happens when Earth reaches a specific point in its orbit around June 21st. The northern hemisphere is bowed at its maximum angle toward the Sun, marking the summer solstice. This data overlay shows the two direct results of this position. First, the North receives the highest intensity of concentrated solar radiation. Second, it experiences the longest duration of daylight of the entire year. In the exact same moment, the Southern Hemisphere faces the opposite mathematical conditions. The solar energy is spread thin, and the daylight hours drop to their minimum, triggering their winter solstice. 6 months later, around December 21st, Earth sweeps to the opposite side of the solar system. Because the 23.5-degree tilt has not moved, the roles completely reverse. The south now leans in, and the north leans away. Halfway between these extremes, around March 21st and September 23rd, the Earth reaches its equinoxes. Here, the planet's tilt is oriented perfectly sideways relative to the Sun. The terminator line, the boundary separating day from night, cuts straight from the North Pole to the South Pole. This chart displays the result of that geometry. At the equinox, the perpendicular alignment ensures that every latitude on Earth receives exactly 12 hours of day and 12 hours of night. At the extreme ends of the planet, this tilt creates conditions where the Sun never actually sets. During its summer months, the North Pole gets locked into a continuous 24-hour cycle of daylight, with the Sun simply circling the horizon. A fixed axial tilt paired with constant forward momentum creates a strict, inescapable calendar of solar extremes that govern the planet. Down on the surface, this orbital geometry dictates what we see when we look up. As Earth shifts its position, the Sun traces entirely different paths, carving higher arcs across our local sky in the summer and lower arcs in the winter. At night, our perspective shifts outward. Because we are moving around the Sun, the dark side of our planet points toward completely different sets of star constellations depending on the month. Early humans mapped this predictability. By tracking the exact positions of these shifting stars, early explorers could calculate their precise location on the planet and navigate across featureless oceans. In regions near the poles, mastering this timeline of extreme light and dark is a matter of survival. research expeditions have to meticulously plan their operations around the months of continuous daylight and the impending months of total darkness. Earth's slanted 365-day journey through space dictates the rhythms of agriculture, drives our global climate patterns, and makes complex life possible on our planet.